Hello, everyone. Welcome to the webinar of today with Technobiz crystallization systems with two guests. We will be streaming from a couple of different countries today. We have myself in the Netherlands, my colleague Carmen Guguda, who will be starting. She is in Germany at this moment. Professor Doris Braun is located in Austria, and Professor Spingler is in Switzerland at this moment. And we have quite an international crowd as well. What you can expect today is a short introduction by Carmen about Technobiz crystallization systems and the crystal breather. And after that, she will introduce both professors and their background, and we will listen to their presentations. Of course, you have the possibility to ask questions. There's this feature in GoToWebinar where you can enter your question, and we will conclude the webinar with a live Q&A with both Professor Braun and Professor Spingler, and we will try to cover all of your questions there. If it's not possible to answer them during this webinar, we will make sure you will receive an answer by email. Or if you later on remember your question or want to ask us something, you can always send us an email, of course. Yeah, thanks a lot for joining us. There are a lot of people in already, and even people still joining, but let's just start because otherwise we will run out of time. I wish you a nice afternoon. Enjoy.
Indeed, this is myself, head of business development and marketing at Crystallization Systems with the company for quite some years now. Yes, you can go to the other one. I would like to first give you a short introduction about Technobiz, who we are for those who do not know yet Technobiz crystallization systems. We are a company located in the Netherlands, but we are active worldwide. As you can see on this map, we have a few colleagues located in US, Canada, in Europe, all over Europe, and in Asia and South America. We work with distributors. We are active since the year of 2005, when the first instrument was brought on the market, the Crystal 16 actually. In our product portfolio, currently we have 3 products, multiple reactor systems that you can heat in a controlled manner, with the possibility to have inline analytics on all these instruments. A few differences between them, of course, in analytics and also in working volume and features. In principle, these are your reactors for crystallization, process development and optimization, and formulation. As I mentioned, 3 products in our product portfolio: the crystalline instrument, which works at a higher scale, 5 milliliters, 8 reactor systems that come with the camera technology that allows you, it works exactly like a microscope, allow really see actually what's going on in the vial. Particle size distribution available, determination, shape, particle count, and if you have a Raman spectrometer, you can connect it to in your lab. You can connect it to the crystalline instrument and actually follow chemical reactions or polymorphic transformations as you would do in a normal case scenario, just that with making use of the crystalline, everything is in line, nothing is in contact with your experiment, with the solution, so you do not have to worry about cross-contamination or cleaning of the probes. Recently launched version 3, actually, the Crystal 16, the new industry standard. A few months ago, we came on the market with this new instrument, and actually what you see now on this slide our third product in our product portfolio, the crystal breather, and it's actually the main product that I wanted to share with you in a few things, a case studies that you can do with the crystal breather. The crystal breather, it was brought on the market a few years back. No, just stay there, Geraldine, thanks. What we would like to share with the world today and starting today is the evaporation setup, which you see it on top of the reactor system, and on top of the evaporation setup you see another one, and that's the vapor diffusion setup. So two different setups that we are bringing now on the market and making them available just to make your work in the lab easier, more controlled, more flexible, and shortly I will also give you a few case studies. Now going to the next slide, thank you very much. A few technical details about the crystal breather. 32 reactors with 8 independent temperature zones. Temperature can be used between -15 to 150 degrees per 8 independent temperature blocks. Turbidity, or transmissivity analysis, it's also available on all the reactors, so you can see exactly when something gets into solution, is dissolved, or when something is crystallized. The evaporation setup, as I mentioned, the vapor diffusion setup, I will explain a bit more into detail on the next slide. And of course, the software, which is in line with our all our product portfolio, easy to use, intuitive, that helps you to set up the experiments and analyze the data quite fast and in a reliable manner. So the instrument comes with the possibility of top steering. This top steering, actually, I think you will also maybe see it, notice it in the slides of Bernhard. It was modified and developed with the time, having feedback from our customers and our users on how to improve it. And we really look into how you can actually reach homogeneous mix but not destroy your crystals. So therefore also top steering, it's this hook is available on this instrument. Evaporation, as I mentioned to you, this evaporation setup, what you see in the middle, comes with an evaporation top specially designed to be able to perform controlled evaporation. You can control it when to be on and off from your software, and also if you connect, actually you need to connect the system to a vacuum pump, so then you will control as well if you want deep vacuum, 200 millibars, 500, depending on what you are, what is your objective. The special design of black top that comes on top of the vials, on the caps, it's actually the beauty of the system that it has an inner micro channel system, allowing each one of the vials to be evaporated separately in such a way not to avoid cross-contamination. So you do not have to worry about cross-contamination between the different vials. And the vapor diffusion, the one that another gadget, actually how I like to call this instrument, the gadget instrument, because it comes with different gadgets, is the vapor diffusion. You see the vapor diffusion there, on the right image, the setup with twice 4 reactors connected via tubing. Well, if you recall the a more classical way of how you would do vapor diffusion, outer vial you will have the anti-solvent, and in the inner vial you will have your compound or a saturated solution in a solvent of your compound. And there you depend a lot on the vapor pressure, actually. The basics behind this crystal you should have as an anti-solvent anti-solvent with low boiling points of high vapor pressure to travel towards the inner vial. By making use of this new setup on the crystal breather, you can actually set your anti-solvent on one side, on one block of 4 reactors, and a compound on the other one. You can now make use actually. So it's your instrument where, of course, any type of solubility screening is available. You can easily do with it. Also, you have the flexibility of the 32 vial, so you can do quite a lot in the same time. It's a very, and the fact that you work a very small volume, 0.06 to 0.1 milliliters. So with only 1 milligram of material, you can do quite a lot actually. It's of course the instrument for single crystal growth and polymorph crystallization type of screening. I will not get into too deep into the single crystal work because there both Doris and Bernhard can give you their feedback on how the instrument can be used and how they experience. I will just go a little bit into the crystallization, and if you go to the next slide, Geraldine. Well, actually, the added value of the Crystal 16, even if you look at the, as you have here, the drug discovery pipeline, is that it works at so small volumes. It's the ideal instrument to be used in early discovery when you have only a few milligrams, 100 milligrams from your chemist, and you need to try to see if it's soluble, in what is soluble, and even to grow single crystals. It's quite important to, if you go to the next slide, to confirm that molecular structure of the compound that you are making or you receive from your colleagues, your chemist. It doesn't matter what you have, if it's a molecule, if it's a polymorphic form, a solvate, you need to click. I didn't realize that has quite some animation. You need to click a bit more. Yes, if it's a salt, the polymorphic forms of the salts or solvates, or a co-crystal. Once again, yes, that's it. Thank you, Geraldine. We always need that nice crystal that we can use to single crystal to determine either by single crystal X-ray diffraction, but nowadays are also other methods. So we look for those perfect crystals. You can go next, and this is the beauty of the crystal breather, that actually it's so versatile, gives you the possibility of varying, making use of different multiple crystallization methods, as you can see here. Cooling, combined cooling, evaporation, vapor diffusion, you name it. It's quite an easy way and reliable way. If I do the experiments today, tomorrow another colleague of mine, if comes, can repeat the instrument, the experiment, and have the same result. This is quite important. Going further to the next slide, I wanted to give you a bit of an example on how you can just envision how you can split the breather, let's say, in different pieces, and how can you design your experiments. And I always make emphasis on the diversity, and through the years in my career I noticed that, and I hear at also different conferences, people advocate for diversity, smart diversity in your design of experiments. If you go to the next one, on how you use your crystallization methods, how you choose the chemical diversity, solvents, and parameters of the crystallization. Here you have a case study where, in a normal case scenario, if you do anti-solvent, cooling, evaporation, slurry type of experiments, what we all do in the lab, you actually would miss quite a number of forms. As you can see here, the different color means different polymorphic forms. For this specific API, if you would not do vapor diffusion type of crystallization, you would miss quite a a lot of forms, which are quite important. If you think from a process development point of view, you wouldn't want to know all the forms available out there to know how to decide or pick up the form that you will take into development. And going further, this is another example. Next slide. Where actually a former API from Sanofi before the group of Lang from Hungary, they played with it. It was known to have only 2 polymorphic forms. And as you can see here, they did a bit of diversity in the crystallization methods, in the solvents, chemically diverse, and they were actually able to obtain 8 forms, 2 of them pseudopolymorphic forms, to call them like that. And the last case that I wanted to share with you are the a comparative study that we did also some time ago in collaboration with the Radboud University, Nijmegen in the Netherlands, where we looked at crystallization screens at microliter scale versus 1 milliliter scale in the crystal 16 with a quite nice compound that could crystallize in multiple different polymorphic forms and shape as well. Beautiful colors as well. And as you can see, of course, depending on the thermodynamic stability of the polymorph, you would, per crystallization method, you would obtain one or the other one. If you go next to the next slide, what actually I wanted to emphasize here is that with the crystal breeder, you do not only use it as a reactor, heat, cool, and make sure the crystallization method is performed in a controlled way, but making use of the transmissivity technology, turbidity, known by others, many of us actually, it tells you when something gets into solution or when something is crystallized. This is quite important to know if you want to repeat or to optimize the process. So, and with this, I'm going to my one of my last slides, where once again, I would like to emphasize on diversity, chemical diversity for the solvent that you are using, depending, of course, highly dependent on the objective that you have. Chemical diversity when you are looking to to find out all those polymorphs forms available for a compound. But for example, if you want to grow single crystals, well, I do still remember what I have first learned when I went to as a student at Radboud University in Nijmegen as a crystallographer. You should look like towards benzene-like solvents, and not long chains or highly volatile. In principle, should be avoided. Of course, crystallization method, as I mentioned, advocated in the last few slides, are quite important. And I'm pretty sure you'll hear much more from Doris in her on her slides on how to grow single crystals, and also from Bernhard. This was a bit of an introduction and some case studies on crystallization and the crystal breeder. And I would like Geraldine to give you back the floor and allow you to introduce Doris.
Thank you, Carmen. Thanks for your story on the crystal breeder and its new modules. We are about to start listening to Professor Doris Braun, who is connected to the Institute of Pharmacy at the University of Innsbruck. it is the university where she both graduated and promoted and did her PhD in natural science. And the current research in Innsbruck focuses on the scientific and applied problems related to solid state properties of pharmaceuticals and other small organic molecules. She used to live in the UK, and she spent years at University College London and the Department of Chemistry, where she was introduced to the world of computational chemistry, and she's now applying both experimental and computational approaches in her research. After the presentation of Doris, we will move on to Professor Spingler. He received his PhD from the University of Basel back in '98 with a summa cum laude, which is of course something to be very proud on. And we're very happy that he wanted to join us today. And he did that on an asymmetric organic synthesis with carbanions. The resume of Professor Spingler is long and very impressive. Since 2016, he's a titular professor at the University of Zurich after gaining years of experience in the field of bioinorganic chemistry, crystallography, and screening. Yeah, we would say let the numbers speak for itself. Professor Spingler has over 180 peer-reviewed publications, a license agreement, a patent application, and over 550 entries in the Cambridge Structured Database, and 19 entries in the Protein Databank. We are very happy that both Professor Braun and Professor Spingler are here with us today, and I will not make you wait any longer and move on to Professor Doris Braun.
Yeah, thank you, Geraldine and Carmen, for this really nice introduction and setting me off perfectly. So I won't say too much of an introduction. So what I will be focusing now on is within this webinar on single crystal perfection tips and tricks on the sublimation and vapor deposition applications using the crystal breeder. So I will briefly start with a short introduction, then move on to some case studies and some concluding remarks. And in the handouts that will also be distributed, you will also find some other really nice literature examples, which I will be skipping in the interest of time for this webinar. So how can we now grow crystal techniques? I would say, can we grow perfect single crystals? I would say the most common technique still is growing those from solution. We start from a homogeneous solution, then hopefully end up with some really nice crystals in solution. Second technique is to grow from liquid from melt, where we can use the equilibrium temperature to grow single crystals, temperature cycling. But my topic of this presentation will be the growth from the vapor phase, so that we simply said evaporate the powder, make sure that we can deposit the vapor onto either a glass or onto seeds. So when we look at the phase diagram, the pressure temperature diagram, where are we? We are starting with a solid compound, and through sublimation, it goes directly into the gas phase. And what we then need, we have to go back, the deposition, and this refers to the process in which a gas changes directly into the solid without going through the liquid state. And just quickly mentioning, what are the advantages of sublimation? First of all, coming from chemistry point we've seen, it's probably the purification process. We have a minimum amount of product loss. And another big advantage for us, especially working in pharma, is that we need a minimum amount of product. Microscale sometimes even works. We don't need solvents. If solvents are present, for example, as residual solvent contents, they are effectively eliminated during the sublimation process. And what's especially for me really of interest is we can produce new polymorphic forms through sublimation. And sometimes we are lucky enough and even get really good single crystals which are suitable for solving structure using standard single crystal experiments. Just to sum it up, what can we see when we do a quick sublimation experiment, as I will showing on one of the next slides as well. And when we are able to have a microscope and can observe it or then watch the products, sometimes it's even possible that on our After our sublimation experiments, we see different morphology, and this is then very often already an indication that we manage to produce different polymorphic forms of a substance. For example, in this picture, you can see different polymorphic forms, and more easily to recognize probably is here based on the different morphologies. And how can we now produce those different forms? It's simply when we perform our sublimation experiments, we have to consider in the temperature gradient, the temperature at which we have our compound and to which we sublime it to. And so we may be able to control which polymorphic form forms. And I will show this to you in one of the later experiments. What's very often happening as a byproduct to the vapor deposition is condensation. We have liquid droplets, but sometimes then they nucleate and we again get crystals, or if you are below the glass transition temperature, we end up with the amorphous phase. So you can see by varying the condition, there's a possibility to get different polymorphic forms, crystalline states, or sometimes we end when we go through the condensation process with a glass state. So just once more, sublimation works very often, and the big advantages are it's at a small scale. We only need few crystals. We end up with chemically and physically pure crystals. So if you take one crystal of this only, and very often we get single crystals, which we then proceed for further experimentation. The biggest disadvantage, I would say, is thermal stability, because normally sublimation occurs close to the melting point temperature of a compound, and if this is very high, especially with the newer APIs, we often observe decomposition. So then sublimation to thermal stability is a problem, but there may be a way around by reducing the pressure that we can lower the sublimation temperature and hopefully still be able to produce nice crystals of our compound via the sublimation and vapor deposition procedure. Something that's also important, especially when you're looking for different polymorphic forms or want to grow a specific crystal, that's the epitaxial growth. And what this is, we take a substrate and this substrate acts as a seed crystal, and the deposited material takes on the lattice structure and orientation identical from the starting material. There's a really nice publication out done jointly by the group at UCL around Professor Sally Price and the experimentalist Professor Alistair Florence. And what they did here, they used the dihydrocarbamazepine crystals as a seed crystal and managed to grow carbamazepine crystals on top of it. And this was the first experiment where they managed to observe form 5. And what's special about this form 5 is the first catameric structure, because the previously known polymorphic forms were all dimeric structure. So that's one of the big successes and a really nice example that shows you how you can use seed crystals of related molecules to produce new polymorphic forms, because those two compounds you can see near the crystals here now, the crystal structure as are isostructural, because as already mentioned here, the sublimed material takes the lattice structure and orientation of the substrate. And I would say that's a big opportunity to produce new polymorphs, seed crystals, which then maybe potentially be used in cooling crystallization experiments for upscaling. But how do we do sublimation experiments? I'm not going through all these examples, but I dig through a little bit the literature. And one of the first sublimation apparatus is this one from 1855, where simply said 2 watch glasses were combined, heat comes from here, and then the sublimed crystals appear, deposit here on the top watch glass. And here, those apparatuses have in common that only heating is possible. I would say the next improvement is then to have a device where you also can apply controlled cooling. And probably most of us are aware of the cold finger apparatus, where we have can use water to cool, for example, the surface here. And so we have, when we apply heat here, a bigger temperature gradient to do the sublimation and vapor deposition experiments. And I would say one of the next improvements is the possibility to reduce the pressure, apply vacuum, because with this additional tool, we can reduce the sublimation temperature and make even compounds which otherwise we would not be able to produce sublime crystals possible to observe the sublimation and then grow nice crystals. And yeah, some of those apparatus you can see here do not look too different to some jacketed vials, which we are still using nowadays very often in our labs. But how do we quickly attempt sublimation experiments here in Innsbruck? So we start with, I would say, fairly uncontrolled experiments using the Kovler hot bench, because what we can do, we can control the temperature here where we put our compound onto, but not the temperature where we sublime it to. Here we have a temperature gradient from 50 to 200 or 250 centigrades. We take less than a micrograms amount of our substance, place it on a microscopic slide, put a spacer in between it, and let the experiment then work at different temperatures here on the hot bench and check whether sublimation occurs or not. So we can quickly estimate without reducing the pressure here, of course, if a compound shows sublimation and at which temperature. A second easy and quick way is using hot stage microscopy, because here we also have the advantage during heating, we immediately see when sublimation, those crystals here would be sublime crystals, different polymorphs again, different morphologies, or also condensation occurs. And here sometimes people are not thinking about it, but when we have the microscopic slide, our material and the cover slide, there's a tiny distance here, a small gradient in temperature, but it's often enough that we see the sublimation experiments. If you then want to go for upscaling, we naturally go into lab, use a sublimation apparatus as shown here, where we can control the temperature here for the cold finger, and also reduce the pressure if we want to. And this was also the idea then to use the crystal breeder to perform sublimation experiments. Some of those pictures, especially this one, you have already been seen. Carmen explained it, so makes it easier for me. But how do we attempt now sublimation experiments? It's very easy. We put portion of milligrams of compounds in one of those vials. And if we want to do the sublimation experiments without reducing the pressure, we just put a second small vial on top of it. And this ring here was just to keep it in place when we transferred it into the breeder. The second option is then we can also make use of the crystal breeder and reduce the pressure to a controlled value and then wait until sublimation occurs. And within the scope of a diploma thesis, we tried several examples, and few of them I'm now sharing with you. The first one was the salicylic acid. Why have we chosen this compound? Because from literature, it's now known to sublime heavily, and sublimation occurs at temperatures slightly above 50 centigrades. We complemented our sublimation experiment with thermal analysis. So the blue curve here gives you the TGA curve. So what we have done, we've taken the compound, heated it up under controlled conditions, and did weighing operations. And so we see mass loss corresponds to the sublimation. And as already mentioned, normally sublimation occurs close to the melting point temperature. And here you can see this was just a quick experiment on the hot bench where we put the sample between two microscopic slides and had a spacer in between. And on the top, we see crystals. But the problem here is they grow extremely quickly, big crystals, too big, but not nice. And there we need now controlled conditions where we can grow beautiful single crystals. So we did crystal breeder experiments. We varied the temperature and whether we used no reduced pressure or we reduced the pressure. And this gives you an idea about the duration of the experiment when we then checked and were satisfied that at least few crystals were observed. What we learned from this example is that at higher temperatures, we have strong sublimation occurring here, but the crystals do not look nice. When we decrease the temperature or potentially reduce also the pressure, we are able to grow some really nice single crystals, which then can be forwarded to standard laboratory single crystal structure analysis with the devices that are around. So this was an example where we know it works. So the next one then, we used a little bit more challenging one, the difenic acid. It shows sublimation, as can again seen here from the TGA curve, mass loss, but if you check here, this is occurring about 200 centigrades, and in the literature it was mentioned that sublimation only occurs above 150. And there we already have problems with organic compounds, because the higher the sublimation temperature or melting point, the more likely it is also that decomposition occurs. And when we want to grow some nice crystals and keep the compound for a longer time at higher temperature, especially carboxylic acid functions will start to decompose. So few experiments that have been undertaken with the crystal breeder. Here I'm showing the variability of temperature and whether reducing pressure helps or not. And here you can see the direct comparison of two experiments where sublimation was undertaken at 150 centigrade. This would be here. We kept the sample for 6 days. Without reducing the pressure, we already see some few crystals, small but not too bad. By reducing the pressure here, we can make sure that more crystals and some really nice ones like this for one we can grow. So that's our advice is, if you have the possibility to reduce the pressure and you have a compound which shows sublimation at a higher temperature, then reduce the pressure. You can have the ability potentially to do the sublimation experiments at a lower temperature and grow more crystals. So I'm quickly jumping to another application. The next system we have chosen is a polymorphic system. And we already learned that we can produce different polymorphic forms by controlling the temperature or the temperature gradient between the temperature where we keep our compound and to which temperature we sublime it to. In the case of this compound, if we had lower temperatures, we manage to produce this so-called form 2, long needles. At higher temperatures, we produce more of these block-shaped crystals, the form 1. We were interested whether we could reproduce those experiments in the crystal breeder, but what I also should mention, those are pretty short experiments. As soon as we sublime for a longer temperature, we mainly produce form 1. So with the crystal breeder, what we've done, we filled our compound once again into those vials, increased the temperature to predefined values, not reducing the pressure or reducing the pressure, and at lower temperature, no sublimation was occurred within up to 1 week. When we went to higher temperatures, here we didn't use the reduced pressure because the compound was colored, and this would have caused then a changing color of the tubes and everything. But still, it worked without reducing the pressure. And the side effect, what we also can see here, I would say fairly quickly, we have different colors here, and those are different polymorphs. So here where we have the sublimed crystals, like most of the crystals, we succeeded in producing polymorph 1 and 2. With this setup at a higher temperature, it was not possible to produce phase pure form 2, mainly because we stayed for too long time at the higher temperatures, not too high. And here you can also see within the crystal breeder, the heating block. Here the temperature was applied, because what we also had with our device, it was tailor-made, that the heating blocks were cut a little bit, that we had a higher temperature gradient. And at the interface here, you see still form 6 is growing, and here the other polymorphs. Why is this? Because at higher temperatures, there I'm going back to a DC curve, we start with form 1. We can induce the phase transformation, and if you keep the compound for a longer time, at, for example, in this temperature range, we also already induce the phase transformation. And with this experiment, indirectly, we could check also the temperature. So here was the temperature gradient for the sublimation experiment. And I think this is a nice example that shows you also then via thermocycling or keeping your compound at certain temperatures, varying the sublimation temperature here on top of it, you can produce different polymorphic forms. And the last example, sorry for quickly jumping to another topic, was using co-sublimation as a co-crystallization technique. Because when we want to produce co-crystals, which are composed of two compounds, are there within the crystal lattice, as exemplarily shown here for paracetamol and oxalic acid. And this table is taken from one of our most recent work, together with the group at Imperial College in London. They did computational screenings for polymorphs. We in Innsbruck here did the experimental work, contrasted it. And for the paracetamol system, there is one co-crystal, which was already known prior we started the work, the oxalic acid. We could reproduce it using the standard techniques, but also this co-sublimation technique. So what have we done? We just have taken roughly molar ratios of the two compounds, put those into the crystal breeder, and then increase the temperature and could collect some co-crystals, single crystals up here. And in this case, the experiment duration was 50 to 20 minutes, and we had one crystal. We checked it with X-ray powder diffraction and could see that it was indeed the same crystal as this one. This won't work all the time. There's some limitation because both of the compounds need to sublime, so at a similar temperature range that then the vapor decomposition can occur. But it's a quick experiment, and if you have the ability, I'm advising to also try this experiment. So that's already the end of my part. So I hope I could show you the sublimation can be easily performed. And in my opinion, it should be included in screening programs, especially if you're looking for different polymorphic forms, but also for co-crystal. What can be extremely tricky when you do sublimation experiments to control the variables, especially temperature and pressure. If you have equipment, like for example, the crystal breeder, this can be easily done. What else? You could modify surface properties onto which surface you are doing a sublimation experiment. So you have more variables that I've shown you. And yeah, with instruments like the breeder, you can easily control the condition. They're highly reproducible. And the ability to reduce the pressure is really valuable if you're performing sublimation experiments, because then for certain compounds, you may be able to do sublimation experiments, which otherwise you couldn't be doing. And just some thanks to especially also to Professor Grieser here in Innsbruck and Magister Karin Meyer, who was a diploma student at the time, who had fun working with one of the crystal breeder, and also to Technobiz, thanks for the collaboration and allowing us to play around with the breeder. And to all of you, thank you for your attention.
Thank you very much, Doris. We received a question. We will cover that during the Q&A. And then we will now move on to Professor Spingler. Thanks a lot, Doris.
I would like to thank also Technobiz and in particular Carmen and Geraldine for giving us the opportunity to present our work in the area of isothermal and especially non-isothermal single crystal growth. Before I will start, I just want to share with you what we are doing apart from crystallization. And as you can see on the bottom slide, we are also working in the field of PDT. However, obviously today I will concentrate on single crystal growth. In the most recent years, and this will be not part of the presentation, we've also started to work with robots. And I just want to highlight our 2018 Chemical Science publication, in which we generated an anion screen to crystallize cations. And actually just this year, together with the industrial collaboration, we managed to crystallize many of everyday's APIs with the help of this screen. But now let's go back to the topic of today. This was already nicely introduced by Carmen and also Doris. I just want to share with you our standard setup, our manual standard setup, what we do for isothermal vapor diffusion. And this is important that we then also later on see the differences with respect to doing crystallization with the crystal breeder. So what we do is we have here our kind of simple recipe. We have an inner container, which you see see that on the lower right, where there is this compound to be crystallized. In this case, it's vitamin B12 because it has a nice color. And normally we take about 4 milligrams of substance. The important point is that we do want to start with a clear solution. And if we don't have a clear solution, we will filter it. Then we'll dissolve it about 0.5 milliliter of solvent in the inner container. And then we put about 2.5 milliliter of the anti-solvent, normally having a higher boiling point, about 5 to 10 degrees higher than the solvent, and place that in the outer container. We then wait for days or weeks, and you also saw in the presentation of Doris that some of this crystallization take quite a while. If nothing happens, you can still unscrew after these 2 weeks the cap a little bit, and then you will change from a vapor diffusion experiment directly into an evaporation experiment. So now the question is, what about non-isothermal crystallization? And the machine already has been introduced quite a bit. Here you see on the lower right actually 2 photographs from us. This is the old style of the crystallization setup, so don't be confused. We just used the old style. You've seen in the presentation of Carmen and Doris the new screw caps. In the end, I wanted to show you these pictures here because you can quite nicely see the experimental setup. So you will see in the left picture, you will see the glass tube. This is transparent, and you see how much down the actual stir bar, or well, it's not a stir bar, the stirring head goes, and you will see a picture of such a cap on the lower right. This can stir, or when we want to do crystallization, obviously we can switch off the stirring so that then undisturbed crystallization takes place. We were fascinated by this machine because it allows this small working volume of about 0.1 milliliter, and thereby you don't need so much material in order to do these crystallization setups. First, we kind of tested it, and it worked very nicely in these indicated settings, just to see whether we could detect clear and cloud point for a standard system. Now let's go right away to the crystallization. The first compound that we tested is carbamazepine, a well-known compound in the crystallization community. And here you already see some differences to the isothermal crystallization, where you use vapor diffusion, a solvent and an anti-solvent. In this experiment here, we only used one solvent. Of course, you could also work with solvent mixtures, but for the simplicity and to start with, we just work with one type of solvent at a time. And this type of solvent then depends or determines how much the solubility is. Obviously, this is solvent dependent if we work with the same compound. You might think that then if we just want to minimize the compound consumption, then cyclohexane, so the lowest example in this table, would be ideal. However, the solubility was so low that we could do the experiment, but in the end, the growing crystals were not big enough for our machine at that time. So essentially, by choosing the solvent, you can then choose how much material you will use. And one important point, and this is different to the isothermal crystallization, is that you need to start at room temperature with the suspension. Because most simplistic, you would start at room temperature, you would heat up your system so that saturation is happening. And then when you slowly cool down, crystallization occurs. Again, at room temperature. Of course, you could also do the experiment in such a way that you would go below room temperature, and this is possible with the machine. But obviously, the easier way is to start with room temperature, go back to room temperature, and in order to observe any crystals, you then obviously need to start with a suspension, so that in the end you again have a solid phase apart from the saturated solution. So these were our conditions which we used. You see the concentrations. And here I can already show you two very nice examples. This is post case CBZ. you see that the concentration actually makes a difference. CBZ crystallizes in different polymorphs, and you can already see here by eye that obviously we crystallize two different polymorphs. One is a very fine needle-like polymorph, the other one is a rather massive three-dimensional crystal. And then we were curious about the crystal quality, because you see in the title that these crystals were actually going relatively fast, within only 6 hours. And you hear quite often that for a good crystal, this needs to take a long time. Well, at least for this system, this was clearly not the case. As you can see on the next slide, here you will see the typical crystallographic parameters. And I want to especially point you at the R-int value of the hydrate form of CBZ, where you see, this is not a typo, the R-int is actually below 1%. I can tell you, like, I've done crystallography for quite some time, and it's very rare to see such a low R-int value. So it is possible to grow crystals with the crystal breeder in a very short time, and you get extremely high quality crystals, as can show me here. On the polymorph which didn't contain any water, which you see in the left column, you saw that we could even collect a complete data set up to 0.6 angstrom. And again, this is something non-standard, because obviously for this you have to use the not so powerful molten wavelengths. You see here also the results from another compound, this PBAB, and this is para-aminobenzoic acid, another very popular compound. And again, here we could grow some very nice crystals. So this is already the summary of what I wanted to share with you today. Well, first of all, if you work isothermal, you can also do that with the crystal breeder. You can change easily the temperature at which you do vapor diffusion experiments. And the main focus of my presentation today was that it is indeed possible to use thermal recrystallization to obtain excellent quality of single crystals, which you can directly use for structural determination. With this, I want to thank, first of all, Philipp Nievergeld, who did the experiments, then Carmen, who already was at that stage helping us with the loan of the machine. I want to thank all the colleagues which have been discussing crystallization issues with me over the last 20 years. I thank my home institution, University of Zurich, and obviously Technobiz. Thank you very much, and I'm looking forward to the Q&A session.
Super. Thank you very much, Bernhard. I hope you all can hear me. Thank you very much, Doris. Thank you for sharing with us and with our attendees today your case studies, your experiences with the crystal breeder. Some more successful, some less, but we are all scientists. We know that if we would have a magic ball, would be nice. Hopefully we have now an instrument that takes us one small step further to success, or at least gives us a bit more control on our crystallization. Really nice results. And Doris, I was also impressed. I didn't know about the co-crystallization by sublimation. It gave me quite an idea, to be sincere, for another study. I think we have received some questions, but just before Geraldine will read the questions for us, one would be, just a very short, what would be the one thing that you say you enjoyed by or you appreciated by having this instrument? What is one, if you would have to choose, one added value of this crystal breeder in crystallizing a compound?
Yeah, if I start, small quantities you can use and work on.
Yeah.
I would add to this, because I also agree with the small quantities, that it's very easy to use, reliable and reproducible.
Super, thank you. Geraldine, you are the one who sees the questions.
Yes, that's true. The question is, Professor Spingler, can you share with us how did the crystal breeder help you growing single crystals?
Yes, I have to say, like at the beginning when we did this experiment, I didn't expect that we would be able to grow such nice crystals within such a short time. And we were very surprised that, as I already presented during my lecture, that after 6 hours, and we even didn't optimize this for speed, we could grow such high quality crystals. Because I thought previously to using the crystal breeder that one would always have to have a slow cooling rates, and obviously this is not the case.
Okay, thank you. There's another question that came in. Do you have any suggestion to get single crystals of a compound that crystallizes in filiform, hair-like, in a filiform habit from aqueous solutions? The one who asks the question says, other solvents give different polymorphs, so I cannot change the solvent. A number of habit modifiers like polymers, cellulose, and surfactants were also not effective.
I didn't really hear the conditions. Can you maybe repeat the experimental conditions?
Yeah. So the question is, do you have suggestions to get single crystals of a compound that crystallizes in filiform habit from aqueous solutions? Other solvents give different polymorphs, so I cannot change the solvent.
If I may answer the question, well, I'm still not completely sure whether pH may play a role, so pH could be changed. And then this is quite known in macromolecular crystallization, one may add organic modifiers, so like just small amounts of particular compounds to modify the crystallization behavior from aqueous solutions. So that would be one suggestion.
Okay, great. Doris,
Yeah,
do you have anything to add?
Or potentially, if possible, can I gather that from organic solvents, polymorphic forms are coming, but mixing organic solvents, water, playing a little bit with the water activity, it may work, but it may not.
So that means give it a good try, right?
Yes.
Another one, does the pre-sub morphology affect the sublimation behavior? If so, how could you control the pre-sub morphology?
It's yes, the morphology, I would say more the particle size substantially can influence the sublimation behavior. If you increase the surface through grinding of the compound, you have a higher chance, especially if you have ever had a badly subliming compound. So what we then tend to do, just grind it, make a huge surface area, then sublimation occurs easier or often quicker.
Okay. Well, questions keep coming in. Let me see. What was the main driving force to get different morphology of CBZ from small defense concentration? From, I think. So what was the main driving force to get different morphology of CBZ from small difference concentration? I think that should be what it says.
As I mentioned, it seems like that the concentration plays an important role on the table, and this I didn't show or didn't mention explicitly. Also, obviously, the solvent plays a different role in. And then the one polymorph, which is not exactly a polymorph, but rather hydrates, so the water content of the solvent could also play a role by generating these hydrates.
Okay. Can we use this for polycrystalline growth?
I'm not sure whether the question for either Boris or me. Yes, as you could see, like different polymorphs could be formed under different experimental conditions. So I would definitely say yes.
Okay, thank you. Sorry if I missed it. This Anthony is writing. In case of the sublimation, what is the realistically least amount possible from powder to obtain crystal? And would this amount be different for difficult to crystallize compounds?
If so which wide is the microgram amount and were successful? It's the only thing you have to make sure when you're using smallest amounts. For example, put in seed crystals, or to make sure that this small amount vapor deposits onto these crystals or a special area in your experiment. But you can try starting with one crystal if you don't have more material.
Okay, I think that makes sense. The last question, and then we have to wrap up, otherwise we get way too much out of time. Will sublimation method improve polycrystalline growth of organic molecules?
Polycrystalline, probably if you do the sublimation experiment really, really quickly, and it for sure depends on the system and on the structure whether polycrystalline growth is possible at all. If there is intergrowth or something, then yes. But as soon as you start to control your conditions and make sure that the crystals grow slowly, it's, I would say, similar or related to solution growth.
Okay, great. Thanks a lot to all the attendees who asked their questions. Yeah, thanks a lot. You're welcome, Krishna. I want to thank you, Doris and Bernhard, for joining us today here in our webinar. And we will be sending you the slides and a recording of this webinar afterwards. You will receive that email tomorrow. If you have any questions afterwards, feel free to send us an email. And yeah, thanks a lot once again for joining us, and we hope to see you around in the next webinar. And in the meantime, we hope you enjoy your evening and your weekend, which is coming up. Thanks a lot. Bye-bye.
Thank you very much. Thank you all. Thank you, Doris. Thank you, Bernhard, for making this possible today. And I just wanted to add one more thing. We come back with our webinars first week of September, with a webinar on formulation presented by Dr. Sophie Jambon from AstraZeneca.
Wow, that is what I call
you all.
spoiler.
Bye.
Bye-bye.